professor in biology and in environmental earth system science here at Stanford. He's the founding and current director of the Department of Global Ecology at the Carnegie Institution. He's also the faculty director at the Jasper Ridge Biological Preserve. Now, Dr. Field's research is distinct in the sense that he's looking at climate change and the effects of climate change, how these effects scale from the molecular level to the global level and vice versa. And I think this unique perspective enables him to integrate multiple disciplines and multiple understandings to get a comprehensive and global view of causes and consequences in climate change. As I said, he's the founding director and current director of the Department of Global Ecology at the Carnegie Institution. He was also elected co-chair of the Working Group 2 of the Intergovernmental Panel on Climate Change, who came out recently with a high-impact report. Dr. Field received many awards. He's a fellow of the American Association in the Advancements of Sciences, a member of the American Academy of Arts and Sciences, and a member of the National Academy. With this, I will ask Chris to come. Thank you.
Thanks, Alfred. Good morning, everyone, and congratulations on making it here so early. I've been involved with the GSEP project over the last 4 or 5 years, and it's really been a great experience. I want to acknowledge a wonderful set of colleagues who have taught me a huge amount and made some really important discoveries, not only about the magnitude of the biomass resource that's potentially available and sustainably available, but also about some other consequences of doing biomass energy. And the last time I spoke to you, I talked about the role of biomass energy production in forcing of climate through mechanisms other than influencing greenhouse gases. And I think that that's a really important topic that I'm not going to focus on today, but has a lot of leverage over the system, and it's really worth thinking about. For me, then, one of the next big eras in climate change research and in climate change policy is going to be developing an understanding about how to deal with these non-greenhouse gas forcings, the climate forcings that are caused by the color of the land surface. Here's the starting point for thinking about the sustainable domain of biomass energy. The NPP is total plant growth integrated on an annual basis. If we take the best estimates based on a combination of satellite and modeling data, it looks like the land on average year produces around 57 billion tons of new plant growth. At the typical energy content of biomass, that's around 2,300 exajoules. The oceans are about equally productive, even though they only have a tiny fraction of the standing biomass. They have a lot more area and a lot more rapid turnover, again about 2,300 exajoules per year. As you know, the magnitude of the global human energy system is around 550 exajoules per year. So on an annual basis, land and ocean each produce approximately 4 times as much potentially usable energy as we use in the human energy system. So the magnitude is really large. The question is how much of that is potentially available, how much is sustainably available, and how much utilization impacts other things that we really care about in the Earth system. So I want to talk about 3 aspects of the sustainable domain for biomass energy. The first is why we care about the sustainable domain. The second is, what are the actual dimensions of the sustainable domain? And then what should we do with the biomass once we get it? And that has a lot of leverage over how much resource you think there is. So in the area of why, there are really 2 big issues. The first is, how does extraction of biomass from natural landscapes or managed landscapes into the energy system influence markets? And the second is, how does it influence non-market ecosystem services, things like biological diversity, maintenance of soil integrity, prevention of erosion, protection of watersheds, stuff like that. And for markets, I think it's important to recognize that we have intensive need for managed ecosystems, primarily through the provision of food. And if you look at the history of real food prices over the last more than 100 years, you see a striking trend. The real price of agricultural commodities has tended downward. This analysis starts in 1875 until about 2000. The authors of this study identify some megatrends, but what's striking is that in the last couple of decades, there is a clear rising trend, both in the short-term fluctuations in global food prices and potentially in what this paper identifies as super trends, which you can see as the heavy dash line in the lower half of the figure. And at least in past super trends, there has been several decades of elevated prices. The big debate in the agricultural economics literature now about whether we're entering an era of permanent scarcity or just extended scarcity over some period of decades where we're likely to see high food prices that are going to be representing competition with any kind of biomass resources. A second really important point for understanding the why of biomass is represented in this photograph that was taken in Peru just a couple of weeks ago by my colleague Greg Asner. And this is clearing of Peruvian rainforest for the establishment of palm oil plantation. We have lots of land that's accessible for biomass agriculture, and I'm going to focus on that later. But if you look throughout the tropics, this is the typical pattern. Most new biomass crops are going into forest where the forest estate, the forest carbon, is released to the atmosphere in the smoke that you see here. That was dramatically demonstrated in a paper that was published just this week by Kim Carlson, Greg Asner, and others. And what Kim concluded is that if you look at the leftmost two bars on the left figure, is that in Kalimantan, giant state in Indonesia, over the last 20 years, basically 90% of the area that's gone into oil palm has come from forests, and only about 10% has come from non-forest aspects. Even more concerning is that Kalimantan has vast areas that have been allocated to future development of biomass resources. And those also are about 90% in forested areas. The key issue here is that when forest is converted to biomass, you get to take advantage of the biomass, but you've lost a vast stock of carbon to the atmosphere as a consequence of just combusting it. You can think of this as a carbon debt. Fargione and colleagues did a carbon debt analysis a few years ago that they published in Science, and the idea is how many years of biomass yield do you need to make up for the biomass that you release to the atmosphere as a consequence of of the combustion of the biomass that was on the site. And what you can see is that for the three bars at the left-hand side of the screen, where we're talking about clearing rainforest to establish biomass, it takes anywhere from about a century to several centuries in order for the biomass yield to repay the carbon losses that are associated with the initial clearing. This kind of biomass agriculture can be an economic benefit for the people who are doing it, but it's a net deficit for the environment and for the atmosphere because it takes so long for this debt to be repaid as a consequence of the carbon income. If we are to figure out any way to sustainably do biomass agriculture in forested areas, we have to find a way to avoid this initial release from combustion. And if there were a way to extract that standing crop of biomass, move it into the energy system, into long-term durable products, this carbon debt could be eliminated or at least dramatically reduced. Let me talk about the what. And there are basically four big places we might go with finding biomass that's sustainably harvested. The first is waste, agricultural residue, urban waste, a wide variety of things that are currently either buried in landfills, burned, or just left in the fields to decompose. Abandoned land, and a lot of the work in our GCEP research has been trying to figure out how much land has been used in the past for agriculture or for grazing and is no longer used and is potentially available. Forests represent a huge stock of biomass, and if we could figure out some way to avoid the carbon debt I was just talking about, forests might be a really nice opportunity. And then it's really important to ask, what's the biomass energy opportunity in current cropland? 40% of the current U.S. corn crop is used for biomass. Should we be using biomass at that level? Should we find ways to increase it? Let me talk for a little bit about the abandoned land question. It's in many ways the most attractive domain for biomass energy, and it's a big one, and it should be a real area of focus. And in the GCEP research that my group's done, especially led by Elliot Campbell, who's now on the faculty at UC Merced, we used historical records to try and figure out worldwide how much land was once used in agriculture, has now been abandoned, and how potentially productive that land is. You can see the total abandoned area in the map on the left and the potential productivity of that land in the map on the right. And if you combine those two, you can see that the total amount of primary production, we convert into energy terms, in global croplands is around between 6 and 7 billion tons of carbon per year, and in pasture it's nearly twice that. And in abandoned lands it's between 2 and 3 billion tons of carbon per year. Now, not all this abandoned land is available for biomass energy. Some of it is in forests where we incur the big carbon debt if it's cleared. Some of it, a lot of it, is under cities, and so it's no longer available for exploitation. And then there's an additional category that we're describing as other in this plot, and it represents somewhere between 1.5 and 2 billion tons of carbon per year. And if we ask how much energy might we move into the energy system as a consequence of using this land, it turns out that it is on the order of something like 30 to 40 exajoules per year. And global energy system's about 550, so this represents something like 6 to 8% of the current global energy system. It's a big number, and it's a big attractive number because this is a part of the biomass estate where we can hope for win-wins. Not only are we providing energy into the energy system, particularly because biomass energy is often storable, but we're also potentially improving degraded lands. We're providing a way to enhance other kinds of ecosystem services. One of the things we've been asking recently is whether, when you do this analysis at the global scale, you miss a lot of potentially accessible lands simply as a consequence of the fact that the data that are available at the global scale are not that highly resolved and of questionable quality sometimes. And so we've just done a new analysis for the United States. And with the United States, you see a striking pattern. The U.S. is essentially the only country in the world that wholesale moved its agriculture from east of the Mississippi to mostly west of the Mississippi. And you can see in the left-hand map that the big concentrations of abandoned land in the U.S. are east of the Mississippi. The consequence of that location is that these are areas, when abandoned from agriculture, typically come back as forest, not as something else, abandoned fields. And because they come back as forests, you have this carbon debt issue that makes them difficult to move into the energy system. But still, when you do this analysis at a higher level of resolution, you do come up with an increase in the amount of land that's available. So when in the U.S. we do a county by county analysis with the most highly resolved data that are available, we end up with an available biomass of an available area of 99 million hectares, representing a total energy content of a little less than 7 exajoules per year. And it's about a 60% increase over the numbers we got earlier based on the global scale analysis. And part of that's a issue of just being able to find more small patches when you look at the county level. And part of it is a problem that when you're working at the global scale, it's really hard to avoid double counting. I can't say for sure whether this 60% increase on the 30 to 40 exajoules I was talking about earlier is going to be global, but it likely is. And so I think the update is that it probably is going to make sense to increase that 30 to 40 exajoules in abandoned land by order 50% once we really are able to dig in more deeply. I want to turn now to the question of what we might get if we think more broadly than just focusing on abandoned land that's not in forests. And there's a really nice paper from the University of Montana group just recently that tries to partition for the continental U.S. the available biomass resources into 4 different categories. A category that you can think of as agricultural extensification, moving biomass area agriculture essentially into abandoned lands, but they have a looser definition of abandoned lands than we've been using. And you can see that for extensification, they end up with 13.5 exajoules compared to the 7 exajoules we got. For forestry, they conclude that there's not a very big opportunity for increasing the area that you do forestry on, only 1.1 exajoules. And for agriculture intensification, this is essentially removing waste products from the fields, stover and things that are currently allowed to decay. You end up with a significant amount of energy potential, 4.1 exajoules. And for forestry intensification, more comprehensive harvest of the material that's taken in forestry, 3.5 exajoules. If you add all those up, they come up to about 20 exajoules per year for the U.S. if you were to use all of them, and that represents, you know, on the order of a fifth of the total U.S. energy requirements on an annual basis. So it's a big, attractive number, and the real challenge is how to use it in a smart, effective way. The final thing I want to talk about in terms of U.S. opportunities is croplands. If you think about the current biomass yield in U.S. corn agriculture in a year when we don't have a terrible drought, it's around 2.2 exajoules of energy content. And there's a big debate now about whether it's smart to convert that to perennials. There are at least 3 advantages you might get from converting this farmland to perennial agriculture. One is that the perennial crops, particularly miscanthus, can have higher yields than corn. Miscanthus has higher yields mainly because it can utilize a longer part of the growing season, being a perennial. Because you've got plants on the fields year-round, there's decreased erosion and decreased risk of erosion during harsh climatic periods. And one of the things that we published 2 years ago was that with perennial crops, you get a slightly cooler U.S. climate than with annual crops, mainly as a consequence of the fact that when the fields are green earlier in the spring and later in the fall, they're actually reflecting more of the sunlight, producing a direct non-greenhouse cooling. On the other hand, there are a number of serious challenges that are market-based that are associated with going into perennial agriculture, and perhaps the 2 most serious ones is that you're focused on a single market. As a producer, you don't have a choice of whether to go into the energy market or the feed market or the food market. And the other thing that's a real challenge for perennial agriculture is that it requires a multi-year commitment with either no or low yields for the first few years of deployment. So it's a real mind shift for American farmers, and I don't think we've seen yet how this balance between the potential advantages and the potential disadvantages of perennial agriculture are going to play out. I'll come back to the issue of food security, which I think in the long run is really going to determine whether or not we want to do perennial agriculture in the U.S. So I want to conclude with a few thoughts on what we actually do with the biomass, and I want to talk about 3 particular areas. The first is the trade-off between using liquid fuels or combustion. I want to say just a few words about the algae opportunity, not very technical words, and then finally I want to conclude with some thoughts on biomass energy with carbon capture and storage, which represents in some ways the overlap between the biomass energy opportunity and the carbon capture and storage opportunity in a way that leads to net negative emissions, an energy system that yields energy to the energy system at the same time it's removing CO2 from the atmosphere. So one of the things that we did as a GSAT project is ask, given current technologies, if you're interested in transportation services, are you better off thinking about biomass as a combustion fuel or as a liquid fuel? And using generation 2000 technologies, if you think about light vehicle transportation, automobile transportation, we concluded that you get substantially more transportation services per hectare of land, if you think about taking whatever your biomass crop is, whether it's corn or miscanthus or anything else, co-firing it with coal in a power plant, using the electricity to charge the batteries in an electric vehicle and doing electric transportation rather than converting the biomass into liquid fuels and powering traditional liquid fuel vehicles. One of the things, the main thing that drives that conclusion is that internal combustion engines are so inefficient, and it's great to hear the progress that's being made in GSEP on increasing the efficiency of internal combustion engines. And if you could triple the efficiency of internal combustion engines, it would shift the balance back the other way and lead to a lot of the advantages of having liquid fuels. The other key issue with combustion versus liquid is illustrated in this cartoon from The Economist, where the idea is that once you think really hard about it, doing liquid fuels for light vehicle transportation, we're kind of locked into it for the short term, but in the long term it probably doesn't make sense. But there are other sectors of the transportation enterprise that we really have no clue how to electrify, and aircraft and heavy vehicles is the best example there. So I think that when we think about the balance between combustion and producing liquid fuels, we want to recognize that there's for the very long term going to be a substantial need for high density fuels like liquids that we don't have options for replacing, at least in the short term, but that at least now the big energy efficiency advantages accrue to electrification and thinking about plants as an energy source, not necessarily as a source of liquid fuel energy. The opportunity that I think we have only begun to think about, and we had a wonderful GSEP workshop on this earlier this year, is trying to think of ways to be more aggressive about solving the climate problem. You know, GSEP is focused on ways to decrease carbon emissions to the atmosphere. Critically important agenda. It's hard to say it's one we're making a huge amount of progress on. And as we go farther and farther into the trajectory of not making a lot of progress on the agenda of reducing emissions, there gets to be a increasing priority on finding ways to remove CO2 from the atmosphere. And those approaches would be especially compelling if we could do it in a way that also fed energy into the energy system. And you even are beginning to see the idea that we would need negative emissions in the energy system in some of the formal scenarios that are used in IPCC and other international assessment processes. The figure here shows the current generation of scenarios used by the IPCC, and the most aggressive of those, which is a 1.5 to 2 degree warming, it's called image 2.6 on this graph, passes from positive net negative emissions for the global economy to positive net emissions to negative net emissions at around 2070. And the idea that we might need an economy that worldwide was a net negative emitter 6 decades from now it's a pretty imposing idea. And the longer we delay in implementing a lot of the technologies that are being developed in GSEP, the more likely a requirement for net negative emissions is. And there are a number of possibilities you could think about for getting net negative emissions. Some involve scrubbing CO2 out of the air and depositing in geological formations. But an incredibly powerful set of technologies involves using plants to remove the CO2 from the air, that's the way plants grow, and then thinking about moving plants into the energy system either through gasification or combustion that produces a concentrated CO2 stream that could be stored and would give us the energy content of the plants without having the CO2 release the atmosphere, moving CO2 from the atmosphere to the plants to the geological storage at the same time we get energy. And based on the GSEP workshop, it seemed like the potential to do that was at the scale maybe at the global domain of order 1 petagram of carbon per year, or something like 1/10 of global emissions. And if we could find a way to operate at that scale or a higher scale, it would really make a big difference. And in some ways, it would open new opportunities for being aggressive about addressing climate change. The final aspect of biomass energy I want to talk about is totally at the conceptual scale, and it's whether or not there's an opportunity with algae. And technically, the issue with algae is relatively simple. Algae grows a lot faster than plants, and if you have an economically appropriate way to corral the algae and to expose it to sunlight, you can potentially end up with a vastly more energy than you could with agriculture. But the great thing about agriculture is that it's a self-assembling factory. You know, you throw a few seeds out on the ground and the infrastructure develops itself. We don't have that capability with algae. But for both algae and for plants, we want to make sure that we recognize a really key feature, and that's that they're amazing chemical factories. And in some ways, thinking about using these chemical factories as a combustion source is a huge waste of chemical diversity. And I think that a real opportunity we ought to focus on is figuring out how to take advantage of the really great chemicals that plants and algae already produce, or that we can modify them to produce. Finally, I want to emphasize that with lots of aspects of the biomass energy endeavor, the focus shouldn't be so much on is there an energy opportunity, but is there a win-win energy opportunity where we can address an environmental problem at the same time we're extracting energy for the energy system. And my favorite potential example with algae concerns cleaning up of dead zones at the estuaries of many major rivers, where the problem is too many nutrients going down the river, creating algal blooms out in the estuaries. If we could find ways to grow biomass algae in a way that remove those nutrients, delivered clean water to the estuaries, we could address both the dead zones and the biomass energy problem. So finally, let me just conclude with kind of an overview of where I think we are. It's important to recognize that with food security, we have what I would characterize as a perfect storm. We've got rising human populations, a consistent increase in the demand for meat-based diets, which requires a lot more land area per human that's supported. We're seeing increasing evidence of pervasive and damaging impacts of climate change on crop yields, and we're trying to move into areas that can produce biomass for biomass energy. I see this as a really big challenge, and it's one that encourages a lot of caution in the application of technologies to extract biomass. It's clear that there are limits on the amount of energy we can get from biomass, but I think that it would probably be better to say not unlimited. You know, in the spirit of GSEP, this is a big resource. It's a resource on the order of 5, 10, maybe even 15% of the global energy system. So it's a big deal. And there are real opportunities for improving abandoned land or for the broader set of things that I characterize as win-wins. And then finally, I just want to emphasize that at the same time, I think it's really important to get the most energy, and combustion or gasification tends to get the most energy. It's also true that plants are amazing chemical factories. We don't want to overlook the fact that maybe what we should do is be replacing industrial processes with plant-based processes as an approach to efficiency. And then finally, I really think the big opportunity for the future that we are just beginning to explore is finding ways to have net carbon negative energy system through technologies like BECCS. It's been a wonderful ride to spend the last several years working on these topics through GSEP, and I just want to conclude by thanking all the colleagues that have taken me along for it. Thanks so much. Do I have time for a question or two?
No, that was great.
Time for a question or two.
Yeah, thanks a lot for this great high-level talk. It's obvious why Chris Field is the theme leader in the bioenergy effort at GSEP. We have time for a few questions. Yes, please.
Speak a little bit about the availability of water for some of these different. Would you speak about the availability of water for some of these different things like abandoned cropland and so forth?
Yeah. So all the analysis that I showed you was based on current levels of yield without irrigation. We know that you can increase yields with irrigation, but just as a general rule, we don't have more water that's available. And so I think that it's, with the exception of a few areas, there are a few areas in Africa and a few areas in South America where there's significant irrigation opportunities. For the biomass estate, my sense is that we should be looking at how much can we get without added irrigation. And globally, I think that availability of fresh water for agriculture is going to be a more and more serious problem, and that we should probably be looking at ways to get the biomass with less water than is currently used.
Sure.
Brian Flannery, thanks, Chris. I think the interest in land use change and sequestration issues in the climate arena started with forestry as a sequestration and then biofuels and what the implications were with land use change. But over the last several years, I think the work Jay Edmonds' group at Joint Global Change Research Institute and the MIT work has shown if you almost even forget about energy and sequestration and just ask what might happen to carbon emissions from changes in carbon stocks in land due to changes in agricultural productivity, agricultural demand, and other land use issues, it could be formidable. So I think we need to expand our horizons broadly. And the other challenge they point out is, if climate policy is hard, land use policy is even harder to think it'll actually be enforced by governments. So I think there's a whole other arena to look at, which is land use per se.
Yeah, well, that was basically where I started. You know, the economic analysis that Jay Edmonds' group does shows that if you have a price on carbon, but you don't apply that to forests, essentially you lose the global forest estate. Forests are cut down everywhere, and that it's only if you have an incentive somewhere in the policy world or the economic world to protect forests, at the same time you put a price on carbon, that you can actually end up with a net benefit for the carbon cycle. One more? Elton?
Chris, can you, two, I think, unrelated ideas, but maybe they're related. Is there a good way to convert a rainforest to ag? Is there an alternative to burning? And could you say just a little bit more, I think in line with what the prior questioner was asking about the opportunity with biochar, which comes and goes in the media as a big opportunity? Yeah,
well, so the issue with tropical forests is complicated because tropical forests provide so many ecosystem services, biodiversity hotspots, protection of watersheds, even important influences on the climate and precipitation. So you want to be really careful when you think about removing rainforests for any purposes. From the carbon cycle perspective, you can think about two different ways that you could utilize rainforest resources in a way that didn't create these big carbon debts. One is to move the biomass directly from the rainforest into the energy system, and if you had, I don't know, co-firing with the biomass, you could certainly begin to address that. It's hard to co-fire just mixed biomass stuff. You take a big efficiency hit. And the other thing you could do is think about extraction of rainforest resources for timber resources, particularly if they go into long-term products. That's been really difficult because most of the biomass in tropical rainforests isn't a high priority species, and most of it's in difficult to get to locations, and so far there hasn't been enough economic incentive to really do thoughtful, sustainable forestry. So in principle you could do it, but I think the bottom line is that you want to be really, really careful before you make a decision about converting rainforest for energy purposes. Biochar, Lena Perkins just finishing her thesis with a big component on biochar and especially comparing biochar with other kinds of BECCS opportunities. And the big question with biochar is that it's a field where more of the information comes from advocates still than from systematic scientific research. And so it looks to me like there's a real biochar opportunity, but it's kind of like biomass. It's a not unlimited biochar opportunity. And in particular, I'm skeptical of the claims that there are lots and lots of places where modest amounts of biochar application can lead to massive increases in carbon storage through kind of a catalytic effect of increasing plant growth. Okay,
so
thanks very much.
Let's thank Chris again for this insightful talk.